So let's get started here. Good evening. My name is Brent Kunderle. I'm the local chapter president for the Wenatchee Valley Erratics, and hopefully you're getting out and looking at some of the geology lately. Hopefully you guys have been well, up until today when it started snowing, it was pretty nice out, but the flowers and hiking was pretty good. But anyway, there was a little bit, just a couple things on the Sandhill Green Festival in March. There was some limited amount of field trips and talks and so forth, but overall I think it went pretty well. I gave a little hike over around Umatilla Rock and around Dry Falls at Sun Lake State Park, and hopefully next year we can enjoy a lot more of that festivity. I've agreed to do a field trip for the Wenatchee Valley Museum and Cultural Center on Saturday, June 4th, and hopefully if we can hold out and not have too much of a COVID presence at that time, that we'll be able to enjoy a field trip. So that's about all I have to say right now. So I'd like to introduce tonight's speaker, and who is Ralph Haugerud. He works as a geologist for the United States Geological Survey, or what we call USGS. He grew up in the Seattle area, went and got his undergraduate degree in geology at Bellingham at Western Washington University, and then got his master's and PhD in geology at the University of Washington, where he did his PhD thesis on the geology, the geology of the North Cascades, which he's going to give us a presentation on tonight. You've probably seen a couple of his publications. One that was co-authored with Roland Tabor and Ralph himself. It was called The Geology of North Cascades, put out through the Mountaineers originally in 1999. And then more recently, a lot of work was put into this map. It's called the Geologic Map of North Cascades Range, Washington, put out by the U.S. Geological Survey in 2009. So without any further, just have Ralph take it away, and he's going to talk about the geology of the North Cascades and how mountains formed and so on. I'll let him take the show over.
Thank you, Brent. Let's see if okay, I pushed the share button also. Okay. Everyone can see my screen and my cursor? Okay. Tonight I want to talk about how mountains are made. And I'm going to speak about the mountains I know best, the North Cascade Range that is out my window. And I want to focus on the topography, the steepness, the big walls and the long ridges that make the North Cascades so much fun. And my answer is going to be that there are many origins of Vocal Reef. Let's dive into it. Here are my conclusions, and we'll come back to these. I won't linger on them now, but in a nutshell, mountains are equal to uplift plus erosion. In the North Cascades, we see the ordinary uplift we might expect in a volcanic arc, plus extraordinary erosion at the south margin of the Cordilleran ice sheet. And I think it's these things together that make the North Cascades so special. Outline of my talk tonight, I'm going to start briefly with the plate tectonic setting, because we are geologists, we start with plate tectonics. Spend some time looking at the topography of the North Cascades and address how old it is. And then go to the sources of recent uplift, which include volcanism, local deformation, and most importantly, changes in lithospheric buoyancy. And I'll spend a lot of time trying to explain that. Then a brief digression on orogeny, and then on to erosion, and talk about meltwater incision at the edge of the Cordilleran ice sheet, about feeding extra ice and water into some of the alpine glacial troughs, about exceptional alpine ice accumulation, and about hard spots that resist erosion. So first, the plate tectonic setting. And I think most of you have seen diagrams like this here in the lower right that show oceanic crust subducting beneath continental crust. The oceanic crust goes down and warms up. And depending on your religion, you can believe either that it melts and makes magma, or that it heats up and drives off the water that rises, and that causes melting, which makes magma. The magma rises, Some of it crystallizes inside the crust to make granitic plutons. Some rises further and erupts. The Cascade Range from Mount Lassen to Mount Garibaldi is such a volcanic arc above a subduction zone. The Juan de Fuca plate off the coast is diving underneath North America. Here's the Cascadia subduction zone margin, and goes to depth and creates magma, which rises and makes volcanoes. The Juan de Fuca plate is moving northeast at about 2 inches a year. These green arrows are the distance it moves on this map in a million years. Tonight, we're going to talk about the North Cascades, west and north of Wenatchee, includes Glacier Peak, Mount Baker. Here's the topography of the region, and with some physiographic names. The North Cascades are the part of the range, in my mind, that's north of basically I-90, Snoqualmie Pass. South of there are the Western Cascades and High Cascades that I mostly speak of as the Southern Cascade Range. We're west of the Columbia Plateau, west of the Okanagan Highland. The North Cascades are separated from the coast mountains by the Fraser River. Otherwise, there's a great deal of continuity geologically. We think of mountains as being high, but the North Cascades aren't especially high. The coast mountains are higher. The Purcell Mountains, part of the Rockies, are higher. The Wallowas are higher. We think of mountains as being steep, and the North Cascades are, although other places are steep as well. I point out that Hell's Canyon is locally quite steep. And mountains have high local or large local relief. And local relief here is you take some arbitrary small area, and I've used a 10-kilometer circular patch, and you find the highest point and the lowest point, and you subtract one from the other. And that gives a measure of how big the mountains are, their local distance from their feet to their heads. And the North Cascades do pretty well on local relief. Other places do well also. The Wallowa Range Front, Hell's Canyon again, parts of the Olympics, especially the Cascade volcanoes. Mount Rainier has lots of local relief. The Okanagan Highlands don't. How old is this uplift, the topography of North Cascades? And the short answer is we really don't know, but I'm going to give you a longer answer. One is we know that there was a major orogeny, a mountain building event in the North Cascades from roughly 100 to about 50 million years ago. We think, although we don't have good data, that in general, mountains tend to erode in a few tens of millions of years. The mountains that were made 100 to 50 million years ago should be gone by now. There is some evidence for younger uplift in the Cascades, and we're going to step through this. First, there appears to have been no rain shadow from the Cascade Range at various times. We can see Jump Off Ridge rising up over the Cascades. We know how young it must be. And we can see older volcanoes that are mostly eroded away. Let's go to the story here. Catherine Methner and colleagues analyzed calcite from concretions in the Chumstick Formation west of Wenatchee. The Chumstick's about 45 million years old. The concretions are that age or younger. And they analyzed the isotopes of oxygen and carbon in the concretions. And from that, they can tell whether or not the rainwater that made the groundwater that made the concretions had come from clouds that had been wrung out by passing over a mountain range or not. It's a long and involved argument. I can't do justice to it, but we can look at younger groundwater carbonates that we know formed after the Cascades uplifted, and they show fairly heavy isotopes. If we look at the older ones in the Chumstick Formation, they show lighter isotopes and suggest that the clouds that made the surface water that made the groundwater had passed over a mountain range, or had not passed over a mountain range, I mean. And that's at about 45 million years ago. George Musto and Estelle Leopold published a paper a few years ago looking at fossil pollen from several localities in southwestern Washington, southeastern Washington, northern Oregon, and Idaho off this map. And they found that for 8 to 6 million year old pollen assemblages, there was no sign of a rain shadow either, that the vegetation east of the Cascades matched the vegetation west, unlike the way things are now. So they saw there was no Cascade Range at that time. I can look south from my house and see Jump Off Ridge south of Wenatchee, made of flows of Columbia River basalt that we know are about 16 million years old. And those flows rise up to the west. We know they were made horizontal. They're congealed puddles of lava. They could have had no slope on them in the beginning. And they now rise to the west, and they're deeply incised. Therefore, that uplift and that incision are younger than the lava flows, 16 million years old. And we can go to Black Buttes west of Mount Baker. And Black Buttes are the remains of a 500,000 to 0.3 million year old volcano. We don't know the age really well. These kinds of rocks are hard to date, but we think they're 500,000 to 30 million years old. And it's mostly eroded away. If you look closely, you can see remnants of the layering, the quaquaversal going in opposite directions, layering on the sides of the volcano. And in your mind's eye, put in the volcano that's now mostly gone. And that's mostly gone in less than 500,000 years. So there's some evidence that topography of the Cascades is fairly young, but it's not real robust. I want to talk now about the sources of that uplift. And we're going to start with volcanism. Because it's obvious, volcanoes pile stuff up and make high ground, Glacier Peak, Mount Rainier, Mount Baker. But as we've seen with the Black Buttes, this high ground doesn't stick around. If you've ever climbed on a Cascade volcano, you'll appreciate that andesitic stratovolcanoes like these are very erodible. They are falling apart continuously. And in the case of the Black Buttes, we can date how rapidly that happens. If we go to a geologic map, we can find out, and I apologize for the complexity of this map, but it was what I had that I could show something on this screen. In the Southern Cascades, south of I-90 and Snoqualmie Pass, the map is all oranges and yellows and whatnot that are colors that meant to show volcanic rocks that are younger than about 40 million years old. And the entire range is mostly volcanic rocks younger than 40 million years old. In the North Cascades, it's all different colors: reds, mustards, greens, blues, which are the colors of older rocks, and the deep pinks are young granites. They're the same age as these volcanic rocks. But there are almost no volcanic rocks younger than 40 million years old in the North Cascades. And we can then say that accumulation of volcanic rock, while it's happening at the stratovolcanoes of Mount Baker and Glacier Peak, is not a significant source of increased elevation of the North Cascades. The range has not been built up by volcanism in the north the way it has in the south. Local folding and faulting has created uplift in the Yakima Fold Belt at the margin of the Cascades. And again, Wenatchee is here at the confluence of the Wenatchee River and the Columbia. I showed a picture of Jump Off Ridge, which is this edge right here, where the basalts rise up. And you can see they're wrapped over a big fold here. These folds have to be younger than the 16-million-year-old basalt that they're made out of, so that they're young uplift. For reference here, this is Bomber Bowl, Mission Ridge ski area. And we can also see that these ridges aren't very steep, except where they've been sharpened by erosion. But these folds are things like the Frenchman Hills anticline, the Saddle Mountains anticline, and the Hog Ranch Nanum Ridge anticline. And these are younger than 16 million years old, and they've made uplift. If we step back, the Hog Ranch Nanum Ridge anticline, we can trace to the northwest. And I think it was Joe Vance who showed me this first, through Mount Stewart, through Whitehorse and Three Fingers west of Darrington, and through the Mount Constitution, San Juan Islands. And this is one of the major highs across the North Cascades. And it looks like it's a fairly young fold, part of the Yakima Fold Belt. Now I want to talk about lithospheric buoyancy, which I think is the major contribution to uplift of the Cascades, north and south, and especially in the north. And to understand it, I want to step over to some other volcanoes, the Hawaiian Islands. And this image from Google Earth doesn't show us enough about water depth, so I'm going to go to a different picture. And this is a pasted together image of a lot of satellite bathymetry and other things. And you can see the islands here from Kauai, Oahu, Maui, Hawaii. And the colors are violets where they're deep, and then blue, and then they go up through green, yellow, green, yellow, up into red as things get shallow. And far away, there's deep water. Over here, there's deep water. And there's a moat of deep water right around the islands. And away from that moat, there's a swell, an outer rise where things come back up again. And what we're seeing in this is the weight of the Hawaiian Islands pressing down the Pacific plate and causing it to flex. And so the islands have pressed, the volcanoes of the islands, pressed down the plate in here. And the plate's got enough rigidity that it doesn't just sink in one place. It bends over a large area. And that bending raises this part out in here. The physics of this are very much like kids on an air mattress in a swimming pool. Here's the Pacific plate. Here's the asthenosphere, the fluid mantle underneath it that the lithosphere floats on. And here are the Hawaiian Islands. I'm sure you recognize Maui and Oahu. The point here is that lithosphere, the rocky outer layers of the earth we walk on, float. And they float on a flowing middle mantle beneath it, the asthenosphere. And the density or buoyancy is all important. It's what makes the lithosphere float. And when you increase the buoyancy of the lithosphere, it floats higher. And that's one of the most important ways we get uplift. To be a little more abstract about it, I'm looking here at a cross section through a piece of the outer layers of the earth. The center of the earth's down below, sky's up here. And geologists use two different sets of vocabulary for the layering of the outer part of the earth. One's compositional and one's mechanical. In compositional terms, the top layer is the crust, and it can be 10 miles or 30 miles thick. It's richer in silica and alumina and alkalis, sodium, potassium, calcium. It's overall granitic in composition. It's got a density of about 2.7 times that of water. The base of the crust is a sharp boundary known as the Mohorovičić discontinuity, or the MOHO. And below that, we know from lots of lines of evidence, is material with a density of about 3.38 that's mostly olivine. It's upper mantle, richer in iron and magnesium in the crust. And it's the richness in iron and magnesium, which are dense, that make it heavier. And as you go below that, the same minerals, the same composition are present, but they get warmer. And as they get warmer, one, expand, and two, they become more fluid. And so the asthenosphere, the middle layer of the mantle here, the mantle keeps on going for a long ways down, has a density of about 3.34, less than that of the overlying colder lithospheric mantle, and it's fluid. If you think about plate tectonics, you don't do this so much, you do this here. And the lithosphere is our tectonic plates. It's essentially rigid, and it's a sandwich or two-layer sandwich of crust over lithospheric mantle. And there's a diffuse boundary above an asthenosphere, which is the same stuff as the upper mantle, but it's warmer and plastic and flows. And it's what the lithosphere floats on. So if you have columns like this, a chunk of lithosphere floating in the asthenosphere, how do you get uplift? One thing you can do is just shorten the entire package. And at that point, it's like stacking two pieces of plywood on. They float a little higher in the puddle than one piece of plywood does. And this is regional folding and faulting. This is classic orogeny, the amount that geologists talk about. You can also not shorten it, but simply stick a granitic pluton into the crust, make a batholith, and you've got more crust. It's low density. It decreases the average density of the lithosphere, so it floats higher. Or you can lose some of this lithospheric mantle. You can make it warmer, so it changes phase from being crystalline to being mushy, and it's no longer attached mechanically to this. And this piece that remains has a lower average density, and it floats up also. In each case, the buoyancy of the lithosphere has increased. Its average density has gone down. It floats higher. If you go to your cartoon of a subduction zone on a magmatic arc fed by the subduction of this plate, we see here that the cartoonist has put in a granitic pluton that's intruding the magmatic arc crust. So it's increasing the volume of low density crust, so it floats higher. And they've also drawn thermal erosion of the lithospheric mantle at the base of the magmatic arc. It's a process that likely increases the height of the arc at this point. And I think that explains those two processes, the granitic intrusion and the loss of lithospheric root by warming, explain the overall height of the Cascade Range. But except for the volcanoes, the North Cascades are higher than the Southern Cascades. And that's something that, to me, demands explanation. And I think the likely reason is that more granitic plutons get added to the crust in the North Cascades than the Southern Cascades. And to explain how this might happen and why I think this, I want to go across the Pacific Ocean to Japan and the Marianas. And on the way there, I want to look at a gravity map of the Northwest. And this is a mess to explain. People go out with weights on springs, and see how much the springs stretch and measure the strength of gravity all over the Earth. And if you put those measurements together, you make a map that shows that the gravity is weaker in the mountains and stronger in Centralia. It's more complicated than that, but this is a Bouguer gravity map, which essentially shows the amount of crust or the density of the crust beneath any given point. And these measurements show, here we've got some blue and then green, and then it gets yellow and red, that the North Cascades have a lower crustal density than the Southern Cascades do. Now let's go across the Pacific Ocean. And we're going to look at density versus depth in two island arcs in the Western Pacific. One is the Izu-Bonin-Mariana Arc, which has a 30-something kilometer thick crust, and it's got a higher density overall than the Northeast Japan Arc, which is a little bit thicker. It's a 35-kilometer thick crust, but it's got a lower density. And this is calculated from lots and lots and lots of measurements of how fast sound waves, earthquake waves, travel through the Earth. The authors of this paper, Kaneko, Mishiro, and Tatsumi, suggested that in the Izu-Bonin-Mariana Arc, the denser crust allows low-density magmas to float higher before they stop rising because they've reached a place where their density matches that of the world around them. Whereas in the Northeast Japan Arc, the crust magmas can't rise as high. As a consequence of the depth to which they can rise, these magmas erupt much larger amounts of volcanic rock. And the volcanic rock then, as we've seen with the Black Buttes, erodes away and is gone. Whereas in this thicker crust, the magmas stop moving at greater depths. As they fractionate, they make less fizzy, volatile-rich magma that can erupt. They make small anesthetic volcanoes that also erode away. But the net result is we get more crustal thickening with time, and this arc will float higher. This one gets less crustal thickening and won't float as high. And I think we have here an analogy for the North Cascades and the Southern Cascades. So recent uplift to the North Cascades. Recent, I'm not quite sure what it means, but I think I'm talking about the last 10 or 15 or 20 million years. Uplift is driven by volcano accumulations, although they don't stick around, they're pretty minor, by local upfolds, by thickening of the crust by arc magmatism, that is granite intrusions, and maybe loss of lithospheric mantle, thermal erosion at the base of the plate by the arc magmas. And maybe, I've not mentioned this, maybe there's some relic elevation from orogeny 100 to 50 million years ago. And that qualification is because our evidence that the Cascades weren't there at 6 million years or 8 million years or 45 billion years is all from south of the North Cascades. They don't really show that the North Cascades weren't there. I think it's likely that the North Cascades are higher than the Cascade Range farther south because the lower density crust of the North Cascades is more effective at trapping arc magmas, which means that we see more magma that congeals as plutons and less than erupts, and that floats the crust higher. So we've been through the plate tectonic setting, topography, sources of uplift. I want to talk just for a little bit about orogeny. Because if you're a geologist, you learn early on that mountain building is orogeny. And orogeny is folding and faulting, magmatism, and metamorphism. The word means mountain building. And if you Google orogeny, you get images like this one, which show folds and faults, lots of plutons, volcanoes, more folding, horrible, ugly, complicated rocks that I've spent most of my career studying the North Cascades. This is what happened in the North Cascades 100 million years ago. And orogeny commonly increases the buoyancy of the lithosphere, mostly by thickening it, and thus creates uplift. But without erosion, orogeny does not by itself create postcard picture mountains. Now, it's unusual that you can make an uplift and not have it erode, but it does happen. The case of the Colorado Plateau comes to mind, or the Chilean Altiplano. And so I think it's worth emphasizing that a thickening of the crust by orogeny alone does not make mountains. You also need to have erosion. Here is an example of an interpretation of North Cascades orogeny by Mike McGroder. And it's a cross-section from the San Juan Islands over to the eastern Pasayten Wilderness. And he's thoughtfully drawn a possible late Cretaceous, so same time, topographic profile. And you'll note that there are no mountains on there, partly because he's humble enough to realize he has no idea what the topography could have looked like 100 million years ago. I spent much of my career looking at these rocks created in this orogeny. They're spectacular. These are the Gardner Mountains, North Gardner and Gardner west of Winthrop. And the top of South Gardner is a big flap of rock that got turned upside down. But I think most has happened long enough ago that any mountains, any uplift that was made has long since been eroded away. So I've basically been speculating for the last 15 minutes. I'm going to move on now and talk about erosion, where we are a little closer to the present. We can see a little more of the processes that happen and be a little more confident of what we're talking about. And I want to talk about meltwater incision at the edge of the Cordilleran ice sheet, about extrabasinal ice and meltwater, locally sourced alpine ice, and hard spots that resist erosion. We know from records in the oceans that in the last 2.5 million years, there have been something like 24 glaciations that affected the Earth. And on land, well, in the Seattle area, we're really lucky we can see signs of 4 of them if we look really hard and squint really hard. In the mountains, we only see the evidence of the last glaciation. And so I'm going to talk about the last glaciation, but it's a set of processes that probably happened over and over and over again in the last 2.5 million years. The Cascade Range is interesting in that we had both alpine glaciation and ice sheet glaciation, Cordilleran ice sheet glaciation, and the two didn't happen at the same time. And in the last glacial cycle, the first thing that happened was alpine glaciation, which is fairly well known in the southeastern North Cascades, from the Yakima Valley to the Entiat. It happened elsewhere, but the record elsewhere has been mostly obliterated by later ice sheet glaciation. And we've got some dating that is not real robust, but indicates generally that these older alpine glaciers were active 20 to 25,000 years ago, more or less. Those glaciers retreated, and we saw the range flooded, at least the northern part of it, by the Cordilleran ice sheet, which reached its maximum extent about 16,000 years ago. It reached, well, out to the edge of the continental shelf, west of the coast, south to Olympia, to just down the Columbia, just below Chelan, out onto the Waterville Plateau, and just beyond Grand Coulee Dam. In the North Cascades, the ice surface was around 7,000 feet high. I was too lazy to make a map that showed this, but things like Mount Shuckson or El Dorado or Mount Baker all would have poked out of the ice sheet as nunataks, or it had little glaciers on them flowing down to join the Cordilleran ice sheet. And the Cordilleran ice sheet in the mountains, we don't see much sign of it, or don't predict much sign of it, much further south than about Glacier Peak. Cordilleran ice did make it up Granite Creek, over Rainy Pass, and down Bridge Creek, and into the Lake Chelan Trough also. I want to look now at our local relief map of the range and look at some of the hot spots, those pink spots where there's more local relief. And I'm going to tell a story about overtopping and incision divides by proglacial meltwater. And we're going to start at Ashnola Pass here in the eastern Pasayten Wilderness, then go to the Lost River Gorge, then the Skagit Gorge, then the Fraser Canyon. And hopefully get some notion as to how it is we can get mountains that are sort of high with really deep valleys between them. I want to go to Ashnola Pass first, and this is where I first began to appreciate what might have happened here. The summer of 1994, my knee went bad, and I was working in the Pasayten Wilderness, and I got to ride with the pack string. Ordinarily, I'm a pedestrian, I don't see the pack string until I meet them at the end of the day. And traveling up Lake Creek, up this valley on the trail, I could, well, it was stony, lots of bare bedrock, big rounded boulders, no dirt, few plants. I could see the sparks from the mule's shoes in broad daylight. And the packer was grumbling because the mules were banging into the rocks and tearing apart his pack boxes. And I could look at this and say, oh, this is a river valley. This is a big mountain torrent. It was dry and hot, and I was thirsty, but it was pretty clear there'd been a lot of water rushing down here that stripped all the dirt off and rounded the rocks. The next day, we went over the divide and got into the head of, and I think it's, I don't know what the name of the creek is up there that flows north into the Ashnola River. And the packer was still unhappy because the mules were stuck in the mud. And as a geologist, it was pretty clear we were walking across an old lake bed. And from that, I understood that at some point during the advance, or more recently in the retreat of the Cordilleran ice sheet, the ice had flowed south up the creek and dammed a lake in here that had spilled over the edge and back down Lake Creek. And the mud the mules were stuck in was the lake bottom sediments. And the day before, I'd been walking the bottom of this rushing torrent. And this is a story not about ice erosion, but about erosion by water directed by the ice. This didn't happen at maximum ice extent. It happened when the ice was advancing and then when it was retreating. And what we see on the ground today is the last bit of retreat. We can go west and see this process happening a little bit larger scale. We go to the Lost River Gorge. Ashnola Pass is over in here. We're going to look at the Lost River Gorge right in here, just north of Mazama. It's a spectacular place that not many of us know because there's no trail in there. You've got to either go cross country up the bottom or be climbing on the high ridges above it and look down into it. So I took Google Earth and I can fly an airplane and look down into it. Here's the Lost River airstrip. Here's the road up around here to Harts Pass. We're looking, the airstrip is the very bottom of the picture. This is the Methow River in here, Harts Pass over here. The present day divide between the Methow, which flows south out of here and down to meet the Columbia Pateras, and the Pasayten, which flows north and crosses the border and joins the Similkameen and flows off the picture out to the north and eventually joins the Columbia, runs something like this. And it crosses a almost level valley floor in here along Hidden Lakes. And it's pretty clear that there used to be a divide that came through here, connecting the high peaks. And that at some point during the Pleistocene, ice flowing south, dammed meltwater in these valleys, the meltwater spilled over a low pass, and with a lot of gradient to it, quickly eroded a deep gorge. And the Lost River Gorge is one of the biggest topographic features in the northeastern Cascades, but because it's negative, we don't see it. Here's John Riedel's drawing of this process. John worked out much of this as part of his PhD dissertation at the Simon Fraser University, and I had the great luck to be on his committee and learn about this from him. But here he shows an early tertiary, late tertiary, so 3 million years ago, east-west divide across the North Cascades. I can't keep my cursor to work here. Then in the beginning of the ice ages, ice advances south, dams the lake in the north flowing valley. The lake spills over the pass and drains to the south and out of Puget Sound, further west, or to the Methow and the Columbia, and erodes a long canyon in here. And the valley down below, oftentimes we see a very deep valley fill from all the debris that was washed out of this canyon. I'm going to go west to one more drainage, to the Skagit Gorge, which is in the North Cascades and has been glaciated. But if you've ever taken a geomorphology class, you learn that glaciated valleys are U-shaped. And this is not a U-shaped valley. It's a classic steep-sided V-shaped canyon carved by a river. And if we again go to Google Earth's airplane, we can look up the Skagit River through the gorge in here, Diablo Lake, and then eventually up to Ross Lake, the Canadian border. And here's the reconstruction process that Ann Crowder drew for Roland and I in our book on the North Cascades. We had an ancient Skagit divide headwaters someplace around Diablo that flowed north into Canada. During the Pleistocene, ice comes up that river, dams it, water spills over the pass, waterfall, rapids, quickly erodes, It makes a deep, narrow gorge. And now today we have the gorge we see, and the divide has moved north into Canada. So one of the things that makes this all work is that, with the exception of the Skagit, much of the North Cascades constitutes an east-west drainage divide along the Canadian border. And we put things together, we think this was the divide. And after this happened, the divides jump north here in the Skagit and here in the Lost River. Again, this is a story of erosion, not by the ice sheet itself, but by water directed by the ice sheet. And then we move west to the biggest one of all, which unfortunately I don't have good pictures for. But there are lots of lines of evidence that are quite robust that show as recently as 1 million years ago, the Fraser, north of the Fraser Canyon, flowed to the north and probably joined the Peace River and flowed out to the Arctic. And at some point after 1 million years ago, the Fraser headwaters something cut through the divide between this north flowing river and the south flowing stream that takes the Fraser out to Vancouver. And the obvious candidate that Andrews et al. Don't point out is glaciation, where we grow a glacier up in here and it ponds meltwater in this area that spills over divide and cuts down through the Fraser Gorge. I find the really telling anecdote about all of this is that in 1754, Alexander Mackenzie and his voyageurs made the first crossing of North America north of Spanish Mexico by canoe. And they paddled across the Continental Divide through a swamp at Prince George, where the only portaging they did was basically over the beaver dams. This is not a narrow divide where steep streams have their headwaters meet. This is one of John Riedel's long sloping valleys eroded by meltwater and then smoothed further by the ice. So we've talked about the origin of the Lost River Gorge, the Skagit Gorge, and the Fraser Canyon, which is overtopping an incision of divides by proglacial meltwater. Now I want to look at the east face of Chopaka Mountain up in here, above the Similkameen, Sinlahikan Coulee, which is another hotspot on the map where there's a lot of local relief. The Chelan Trough and the Icicle Canyon, also hotspots. Here's a view of the east face of Chopaka Mountain, and the coulee is in here. If it wasn't for this coulee, this would be another part of the Okanagan upland and it would not look so impressive. What makes this spectacular, I mean, this peak is 8,000 feet high, is this really, really deep trough eroded across the foot of the slope. Go back and it's this thing in here. We can look at it on a shaded relief map. And here's the Similkameen, and this is the Sinlahikan Coulee below Chopaka Mountain. And it's pretty easy to visualize. This is the Okanagan Valley here, that during advance of the Okanagan level of Cordilleran ice, and also during retreat, ice would have occupied the valley bottom and forced any meltwater present to flow along its side. And that meltwater has carved the coulee, and it's that coulee that makes the local relief in here. So again, this is ice-directed meltwater, not ice itself doing the erosion. In the Chelan and the Methow valleys, it's quite clear that the Cordilleran ice sheet flowed over the divides here up Granite Creek, across Rainy Pass, down Bridge Creek, into the Chelan Trough. We had similar flow across the divides at Robinson Pass, above the Lost River Gorge, Hidden Lakes, up Lake Creek, feeding the Methow Trough. And these big fjord-like valleys are a constant all around the Cascades and through the Coast Mountains. These are unusually well developed. I think it's because they were not carved just by local alpine glaciation, but they saw additional input during the Cordilleran phase of meltwater and ice coming from outside the drainage basin, flowing into it and becoming essentially a local glacier, carving more effectively. Now I want to go down south of the Cordilleran ice extent. Cordilleran ice made it to Lake Chelan, Chelan Trough, Glacier Peak, and look at these valleys here in the Yakima, the Wenatchee, and the Entiat, all of which had alpine glaciers in them before the Cordilleran ice sheet got here. And there's a fairly consistent pattern where the further north you go, the lower the elevation of the ice terminus is. So Yakima, about 600 meters, Entiat at 480, Wenatchee at 500. The Icicle Glacier is an exception to that, and it's got a much lower terminus. And the obvious thing that's happened is that you've got a greater snow accumulation here, basically on the shady side of the Hog Ranch Nannan Ridge uplift, on the backside of Mount Stewart, the enchantments. And that's driven this big icicle glacier system that's carved this incredible icicle canyon, which is one of the conspicuous hotspots on the local relief map. We can look at some other hotspots: Mount Hosamine, Mount Shuckson, Whitehorse Mountain and Three Fingers, Mount Index and Mount Bering. And these are things that wouldn't erode. These are all places where a shell of older rock is surrounding a granite body, a Cascade Arc pluton. And the older rock has been baked hard by the pluton, and it doesn't erode as readily. And again, this is a Joe Vance idea, but it explains some of the hotspots on this map. And then we have other hotspots, Mount Baker and Glacier Peak, which are indeed volcanic accumulation, but we can expect that they're not long for this world. Another few 100,000 years, they should be gone. So we can conclude then that local relief in the North Cascades Range was made by a combination of ordinary uplift in a volcanic arc, and extraordinary erosion at the south margin of the Corrigan ice sheet, and some other factors. In detail, these are volcanism, which builds short-lived high spots, local upfolds, such as the Hog Ranch Nannan Ridge anticline, thickening of the crust by arc magmatism, the intrusion of the Cascade Arc plutons, probably loss of lithospheric mantle by thermal erosion at the base of the lithosphere, above the heat plume coming off the downgoing slab. We can speculate the North Cascades Range was uplifted more than the Cascade Range farther south, because lower density crust in the North Cascades is more effective at trapping arc magmas. So this process here, the third one, thickening the crust, works better in the North Cascades than the Southern Cascades. And there's some possibility, which I don't think is too likely, but I can't rule it out, that some of the increased elevation in the North Cascades is relic from orogeny 100 million to 50 million years ago. But where we can speak with confidence, and what I think makes the Cascades so unusual compared to other mountain ranges of the size, is the role of erosion at the south margin of the Corrigan ice sheet. In some ways, the North Cascades aren't a mountain range, they're an assembly of canyons. Canyons made by meltwater flowing over divides, meltwater that was ponded in front of the ice sheet. This is the case in the tributaries to the Methow, the Skagit, and all the streams that flow into it, and the Fraser. We also see erosion by ice marginal meltwater being locally important. And we see that some of the troughs in the range may have gotten more than their fair share of ice and meltwater for pseudo-alpine erosion, glacial erosion. Icicle Canyon is a special case that's probably greater ice accumulation on the Nannan Ridge uplift. And then we see there are hard spots around the some granite intrusions that also explain why there's high ground. My conclusion then is the North Cascades are ordinary arc uplift and extraordinary glacier-induced erosion. Thank you.
All right, thanks so much, Ralph, for that great talk. I'm just seeing one question here from Kelsey Stanton. It says, great analogies. Will you speculate what causes the crustal density differences between North and South Cascades?
The North Cascades have, it would be really nice to know what's underneath Mount Rainier or underneath Stampede Pass or White Pass. But we think that the Columbia embayment, which is sort of central and southwestern Washington and central and northwestern Oregon, is perhaps even trapped oceanic crust surrounded by older continental crust in the North Cascades, over around Moscow in the Blue Mountains and the Klamath Mountains. And it's got less history, less orogeny, less remelting, less intrusion. And it's, as crust, it's probably thinner and denser. To rephrase that, it's that orogeny 50 to 100 million years ago that made the North Cascades have a low density crust. And there isn't a similar history, we think, further south.
Another question here in in the chats was that wants a little bit more explanation on how Tumwater Canyon formed.
Oh, I've thought about that a lot the last couple of years. I've been working on trying to understand better the sandstones that make up the Shastan Pinnacles and the area around Leavenworth and north to Plain and south to Wenatchee. And it's been long recognized that Tumwater Canyon is an anomaly because the river ought to flow through the soft stuff, the sandstone to the east, and it doesn't. And it's kind of a classic place for this. It's pretty clear that at some point there must have been a fairly flat plain the river wandered across the Wenatchee River where it chose to at will. Something like the the Mississippi does today, or the Platte, that it flowed across a low relief landscape and its course was not driven by where the rock was soft or where the rock was hard, where the rock was folding up, where the rock was folding down. And then at some point, I mean, it found a course that was irrespective of the rock underneath it. At some point there was uplift and the river began to cut down wherever it was. And it happened to cut down through hard stuff instead of soft stuff. And so it made the canyon at Tumwater Canyon. Above there, it's in soft rock, Lake Wenatchee, and there's no canyon. And below there, from Leavenworth below, it's in soft rock and there's no canyon. But Tumwater Canyon is where the river somehow managed to get stuck cutting through hard stuff.
All right. Great. Well, thanks so much again. I don't see any other things in the chat, nothing in the question and answers. So with that, I guess we'll end the program. Thank you very much for attending.
Thank you all.
Yeah, I might unmute myself. I want to talk to you. Thanks again, Ralph.
You're welcome.
Give me a call when you get some free time, and we can go out in the field one of these days after your presentation. I know you're busy now, so.
Yeah. Yeah, I also have another favor to ask of you, Brett, but I'll give you a call tomorrow.
Okay, yeah, sounds good.
I need a reviewer.
What's that?
I need a reviewer for some local geology. You'd be a good person.
Thanks, Teresa, for your help setting this all up.
Yeah, thank you.
All
There
right.
was a total of, believe me, 39 people.
Okay, yeah, and us three makes 42, I guess.
Yeah.
All right.
Alrighty, have a good night. Thank you.
Yeah, you too, thanks.
Good night.
Night.
Mm.